This is going to be much more important and a bit harder than what we have discussed so far. So please be careful. I believe you know this one also from high school, but you haven't derived it, I'm guessing. Energy stored in capacitors. So let's say I take a parallel plate capacitor like this, and I will charge this one plus Q, this one minus Q, and the distance is D. All right? But of course, it hasn't been that way all along. It used to be 0, then we have arrived at this point. So let me just take this one over here, duplicate it. We went there slowly, right? We started from 0, and every time it was plus Q, we took dq from here and we took it all the way here, right? By doing this from 0 to Q, we arrived at this situation. So how much work have we done on the system? So work done on the system will be change in the potential energy, plus sign, right? That way, we are going to find the potential energy of this final system. Let me just write, this is the intermediate stage, this is the final stage. And we are wondering what is the energy, potential energy of the final state. And initial state where it is 0, potential energy is set to 0. So, good. Can I write that the work done to transfer this dq from here to here is dq times v, the potential difference at that particular situation? Yes, we can. And what is this potential difference? How can you write down v for me? What is v? What is v in this situation? Let's say you know the capacitance. Capacitance is C. So you know that the capacitance is C and it doesn't change throughout the process, right? So V is equal to Q over C, right? At any moment, exactly, dW, the tiny bit of work done, is Q over C times dQ. Now I can integrate it. I will put prime here so that I go from 0 to W. Okay. Let me go from 0 to Q. What do I get? I get the work done to be Q squared over 2C. And this work done is equal to the potential energy. So the potential energy of a capacitor is Q squared over 2C, or it is 1/2 CV squared, or it is 1/2 QV. Do you see? I'm employing Q equals CV here. Q equals CV. So the potential energy is Q squared over 2C, which is equal to 1/2 CV squared, which is equal to 1/2 QV. You already knew this before, right? Now you see, now you know the derivation. Do you have any questions? No? Good. All right. Then let me introduce you to yet another very important thing. Electric field energy. So when we are charging a capacitor, we can actually rephrase it in a certain way. We can say that we are putting the energy into the electric field, because capacitors have electric field within them, and that electric field is holding energy. Okay, what we are going to find is the energy density. So let me write it down. Oops. Energy density, which is energy per volume. I will denote it by U, small u, and this is U over V, where this is volume. Sorry for using the same letters. This is energy. Okay, capacitors are good circuit elements to investigate this because they have uniform electric field. At least we can assume that they have uniform electric field. So if you take a large enough capacitor, let's say with a distance d and area A, if it's a parallel plate capacitor, you can assume that the electric field is uniform throughout this object. Do you have any questions here at this moment? No. So we have already learned that U is Q squared over 2C, right? So what is small u? Can I say that small u is U divided by A times D? Because that's the volume in between. Then U is equal to Q squared over 2C over A times D. Right? Or you can write it down like this: 1/2 CV squared over AD. Everything works here. But we are going somewhere more elegant. And to go that place, we need to use this formula, one more formula. This is potential. Potential is equal to E times D. Do you agree with this? The potential difference is electric field times the distance. Do you agree with this? Everyone? Yes? Good. Then I'm going to put it in. So I have 1/2 times, let me also use this formula, epsilon 0 A over D. You see I'm doing this juggling of formulas, nothing else. So A goes away, D's go away, and I arrive at a very elegant formula which just gives me the energy density that I would have in an electric field. It turns out that the energy density of an electric field of uniform electric field of magnitude E is simply 1/2 epsilon 0 times E squared. So energy density of electric field is proportional to its amplitude squared. So far so good? Everyone is happy? Yes? Good. Let me think what is being asked here. Do I want to solve this problem or I don't want to solve this problem? I think I don't. It's too complicated. This is what it was. It's in the notes. So I will skip it. Instead, I'm going to solve something else. Yes.
What's the difference between energy stored and density of energy?
What is the difference between energy?
Energy stored, like in
U,
so
the big U and the small u.
yeah.
The only difference is one is big U, the total energy, and the other one is energy per volume. Okay? Very good. So, let me ask you this situation. So, I have a capacitor and it has a distance of x, and there is plus q and there is minus q, and it's not connected. This is very important. In exams, please read it very carefully. Not connected to a battery. Okay, right, it's not connected to a battery. And what I'm doing is I'm starting from this point A, where the system sits like this, to point B, where it is plus q here, minus q here. So what is the effect of this not being connected to a battery? You already see that effect. What is? Q remains the same. If it would have been connected to the battery, then would Q increase or decrease? There are lots of different answers.
Is equal to epsilon 0 A over Z.
Yes.
So if you increase D,
Yes.
since the voltage remains
The same.
I mean, Q must decrease because C is decreasing.
Did you follow that? So if it was connected to a battery, then the battery would make sure that the potential difference is the same amount of V, right? But since when you take it apart, the capacitance decreases because the capacitance is epsilon 0 A over D. So D increases, capacitance decreases, so Q decreases. Where does Q go? Very good idea, but no.
What was the question?
Where does Q go?
Go back to the battery.
Back to the battery. You are charging the battery. Okay? Next time your phone is dead, just take plus Q and minus Q and separate it. All right. So I'm going from the situation A to the situation B. The question is, first of all, can you find the potential energy in both cases? Let's find the potential energy UA. What is UA?
Minus integral ft instead of sine.
Why did you say minus into? Why did you say minus?
Wasn't it like that?
Don't worry, everything is fine. Yes.
Because I remember.
So we already have a formula for the potential energy, right? It's Q squared over 2C. So it's Q squared over 2C, which is Q squared over 2 times epsilon 0 A over X. So it is Q squared X over 2 epsilon 0 A. Any objection to this? No? How about UB? Q squared over 2C prime, I can call it prime, which is Q squared over 2 epsilon 0 A over 3X, which is 3Q squared X over 2 epsilon 0 A. So it seems like the potential energy has increased. Right? when that happens, when the potential energy increases, when you do something that the system wants to do or when the system doesn't want to do? The second one. So if you look at these capacitors, do they actually want to come together? Yes. So you are doing something against that. So everything checks out, right? Good. Now let's find it. Let's find the same thing by finding the work done. Let's this time approach this problem in the following fashion. This time I'm looking at it this way. Let's say there is a distance y. When the distance is y, I will find the force required to separate it, and then I will find w integral fy dy, and will hope that I will go from x to 3x, and I will hope that it will be equal to ub minus ua. Do you think, does it look like a plan to you? Do you understand what's going on? Should I repeat myself? So I'm doing the same problem. I start from x and I go to 3x, but this time I'm going to find the work done. And my first step is to find the force that I need to apply at any distance y. Yes?
I have a stupid question.
No stupid questions here.
Like, I
Yes.
just accepted that we are taking integrals, and I don't know why.
Okay, let's remind ourselves, right? We are taking integrals whenever our function is changing with respect to our variables. Okay? So, for example, we didn't take integral here. We just said v is equal to e times d. Although we usually did find the potential differences by integrating e dot dl's, right? We didn't do it here. Why? E was constant. Okay?
But
Now,
it is changing. Kind of.
no, the d is not changing in a sense that, okay, let's go from the top point to the bottom point. Electric field is the same everywhere, right? So in this particular case, we are going x and dx, right? X, we are varying x from 0 to d, right? Yes, it is changing, but your formula is practically e times dx integral from 0 to d, right?
It's the same.
It's not like you are not even when you are not taking integral, you are taking integral. It's just the integral of 1,
Yes.
okay, of a constant. If it gives you any peace with the integrals. Good. The tricky part here, a little bit tricky part, is to find fy. Finding fy here is a bit tricky. Okay. Can you find fy? How would you find fy? Fy is the force I need to apply to make sure that I can separate these capacitors. Yes.
Maybe we can find force electrical fields.
Yes, very good. So can you find electric? So you are saying that Fy is simply Q times the electric field, which changes with Y, right? Changed. So can you find electric field? That's the tricky part.
Cylindrical Gaussian surface
Cylindrical Gauss surface. Where do you put your cylindrical Gauss surface?
around minus Q base.
Around minus Q. Yes?
Is it going good?
It's going very well. So you are doing E times A equals to Q over epsilon 0, right? So E is equal to A over epsilon 0. By the way, the force is not changing, apparently, with distance. You didn't need the integral. Do you see it?
Yeah.
Yes?
I'm just confused about
The electric field.
no Gauss's surface.
Okay, we will come. You should be. So, do you buy this? This corresponds to the. Oh, by the way, we already made the mistake. What is the mistake here?
Minus
So, okay.
Is it A?
Let me tell you what is our mistake. This electric field is correct. There is an electric field in between, which is sigma over epsilon 0. Gauss's law works. We actually found the relevant electric field. But half of this electric field is created by the top plate. Let me repeat. Half of this electric field is created by the top plate, and it can't interact with the electric field that it itself creates. Are you following? No?
No,
Yeah.
I am, but I can't understand what.
Okay. Let's remind you.
This is hard to think.
Yes, it's hard to think, and maybe I'm not doing a very good job of explaining it, but let me use some colors. Enes, you said something. Can you please repeat? No, not something that complicated. Let me tell you just. So, this is minus q. The minus q is creating sigma over 2 epsilon 0 this direction, right? Sigma over 2 epsilon 0 this direction, and this plus q also over here, sigma over 2 epsilon 0. And the blue one is plus q, it's creating sigma over 2 epsilon 0, sigma over 2 epsilon 0, and sigma over 2 epsilon 0. So if you sum them up, you get 0 here, sum them up, you get 0 here, sum them up, you get sigma over 2 epsilon 0, sigma over epsilon 0 in this direction. You see? So what FF found is this total electric field created by both of them, right? However, this plus charge, plus q, is not going to be affected by this electric field. Yes? So it's going to be affected only by this electric field. So the electric field in question here is the red one. And the electric field that is going to enter our equation over here is the red one.
It's like a charge cannot repel or anything.
Yes, exactly. Okay? I hope this was clear to you. So Q over 2 epsilon 0 A is the force, is the electric field. Hence, the force does not depend on distance, and it's just simply Q squared over 2 epsilon 0 A. We can just integrate it. Work done is Fy dy integral. Turns out we didn't need the integral. It's just simply Q squared over 2 epsilon 0 A, 3x minus x, and we get Q squared over epsilon 0 A. Okay? Yes.
Why do we found when we just look at the one part of the capacitor that Q over A q over 8 times epsilon 0. I mean, we use Gauss surface, then shouldn't we found the divided by 2?
All right. When we used Gauss's law here, okay, we actually found the correct answer. The correct answer is that indeed, there is a total electric field that is that much in between. But right at the place where plus q is, you see, this Gauss's surface is not touching here. This is in between. Right at the point where we have the plus q, if you can see, right at that point, we have zero contribution from this one, because over here it's down, over here it's up. Must be zero at the top of itself. You see, there is a singularity there. There is a fundamental problem there. But do you see my point? Everybody sees my point? Yes? Yes.
Can you come down?
Yes, I can come
Where
now.
did the x go from the
3x minus x is 2x.
Yes, but we can
Yes,
split the
x-
two,
X is here.
And I have another question.
Yes.
Can we put the Gaussian surface in the plus q charge? We get same thing, right? Around it.
Do you want to put Gauss's surface right on top of here?
I mean, no, the same thing, not touching minus q.
Yes. Not touching minus
Just
q.
the same thing, but above.
You want it to put it here.
No. Hocam aynısı sadece artı q ortadan geçecek. Hani eksi q değil mi? Artı q'nun ortasından geçecek.
Tamam, ben de onu diyorum. So you want to put it here.
Yes.
Yes?
Yes.
Okay, don't do that. Okay, because then you are wandering on the edges
No, but
and you can fall down.
not the surfaces on the charge. Just the same with this picture.
Hocam
Just the same, but
Ortadan geçecek yine artı q.
right in the middle, you mean?
Evet.
It doesn't matter
Doesn't matter.
because the electric field is uniform.
Ha.
Do you think that this is just a little bit closer to upper side? Do you feel like it
Mhm.
makes a difference? No, it doesn't make a difference.
Hepsini patlasak.
If you do this, the whole thing,
Yes.
then you get no result because you get enclosed charge to be zero and the electric fields are zero. Okay.
Hocam, but I didn't
In general, let me tell you something. Whenever you have multiple plates, okay, please use Gauss's law for individual plates and not the whole system. Okay? Individual plates, then you do the superposition. If you do it for the whole system, you will still get correct answers, but you will get confused by a lot of things. Any other questions? Here?
Hocam, I still didn't
Sorry.
understand why we put it on minus q. Like, why minus?
Because, okay, very good. We could have put it like this. That's also the same thing.
Yes.
That's also the same thing.
I was asking that.
Okay. You could put it like this, but what we are doing here is we are already using something that we already know from superposition from beforehand. Okay, we already are using the fact that we know that there is no electric field here, but
Yes.
some electric field here.
Mhm.
What if this is plus, besides the capacitors? Okay, what if this is plus 2q and this is minus q? Then all hell breaks loose, right? Did you follow this? Yes? It's a different story. So, let me rephrase it. When you have multiple plates, use Gauss's law, please, for each one separately. Your question?
The Gaussian surface here doesn't cover the whole plate, so how it enclose the whole cube?
Yes. Let me just rephrase. Don't use it like this. Efe used it and I agreed, right? He's not the guilty one. Yeah.
I am also confused at this point.
Is this wrong?
Huh?
Is this wrong?
Oh, come on. So far, nothing that we did is wrong.
You said we made a mistake here.
Okay, philosophical question. Does every mistake lead to something wrong? Sometimes you can make a mistake, and can you get a right answer by mistake? Yes. So what we are doing here, just we have wandered around, came back home. We have our coffee. We are going to drink it. When you are going to drink it at home today, okay, remember multiple plates, separately do Gauss's law, then combine them. Forget everything else. Okay? One. Second one, when you are dealing with the force on one plate, make sure that you remove the effect of that plate. Yes? Those are two lessons from this question. Are you less confused now, Efe?
Yes.
Yes. Forget about everything else. So, do we have our answer properly? Yes, we do, because as you can see, if you write down UA minus UB, UB minus UA is Q squared X over epsilon 0 A, 3 over 2 minus 1 over 2, and you get Q squared X over epsilon 0 A. So UB minus UA is indeed equal to W. All right? Any questions? No questions? Okay, let's have the quiz now, and then we will linger on this problem a bit further.